Thanks eGlobal for having me as Scroll. Excited to talk to the devs about the Scroll Messenger and also deploying on Scroll. Oops. Yeah. So we're going to talk a little bit about zero knowledge and scaling Ethereum, being the reason why Scroll is in this space. What is Scroll? Talk a little bit about rollups, and then we will dive into the bridge side of things, which is the Scroll Messenger. Short intro about myself. I'm Raza, a coding nerd. You can find me everywhere at Raza Codes, and definitely check out scroll.io. As a quick notification to everyone, if you have a question or anything is not clear, please feel free to interrupt me. Would love to answer anything as we go. And also a quick reminder on our prizes. We've got 20K in prizes, a prize pool of 4K, which means you just deploy and verify your smart contract, and you're already eligible for a part of the prize pool. We've got 3 prizes of 2K per team and 10 prizes of 1K per team. You can read the criteria here. They're also on the ETHGlobal website. And if you have any questions regarding them, feel free to approach me either on Twitter or we have a Telegram group, which I will just quickly share inside the chat. So if you have a need of, let's say, testnet ETH, or if you have any questions, feel free to join this Telegram group, and the Scroll team will be there to answer any questions. So let's dive into it. ZK rollups. We're going to talk a little bit about rollups and the distinguishments between rollups, ZK rollups specifically, as mentioned by Vitalik, the holy grail of scaling solutions. So very quickly, what is a rollup? I won't dive into too deep. I mean, crypto Twitter is always added and everyone has their definition, but simply put, a rollup batches transactions off chain, so not on an L1 being Ethereum, and then posts the resulting data on chain, meaning in this case, L1 Ethereum. So how does this solve scalability problems? Well, an L1 doesn't need to re-execute the transactions. However, an L1 does need to prove that these transactions have been processed correctly. And typically there are 2 types of proofs, validity proofs, which we will talk about, and fraud proofs. If you're familiar with optimistic rollups, they utilize fraud proofs and they work slightly different, but we won't talk about optimistic rollups in this talk, as the time is obviously limited. So validity proofs are utilized in a ZK rollup. A ZK rollup submits transactions together with a ZK proof that the transactions are valid. And a ZK rollup will generate this ZK proofs primarily to prove the states and that everything is updated correctly. So Ethereum knows, hey, the transactions are correct. But how does Ethereum know it? Well, that's because on Ethereum, there's a smart contract that can verify the transactions, verify the proof along with the transactions that are posted on that smart contract. So typically speaking, if you look at the ZK rollup space right now, this is a graph from the article from Vitalik, where he explained the different types of ZK EVMs, ZK rollups out there. I usually like to look at it simplified like this, and I'll touch upon in a moment why this is important. So typically speaking, right now, if you look at all the different types of ZK rollups, you can either be very close to Ethereum, i.e. being EVM compatible, or there's a trade-off to be made in the performance, the time to generate a proof. Now, what does this mean? To generate a zero-knowledge proof requires quite a bit of computation and overhead. So if we go back, you can see that as you move down in the type, i.e. you go closer to type 1, it takes a long time to generate the proof. That's because if a ZK rollup wants to stay close to the EVM, i.e. act and behave just like Ethereum, it takes a long time to generate the proof because of all the behaviors that needs to be proven that would normally occur for a smart contract in EVM. If you would pick a different type of virtual machine, the trade-off is that you wouldn't have an EVM compatible chain, but you'd be able to generate faster proofs. Now, if you look at the typical examples, typical qualification, it's usually EVM compatible versus language compatible. ZK rollups. An example of language compatible is Starkware and ZK Sync, and EVM compatible being Ethereum. So why would you choose for EVM compatible even though it takes a longer time to generate proofs? Well, that is because you as a developer will be able to use all your existing skills, i.e. Yule, Solidity, Viper, and your existing dev tools, just the way you would utilize them on Ethereum. So the major benefit of EVM compatibility is that even though the performance, the time to generate a proof takes longer, for the developer experience is much more pleasant because it's a lift and shift from what you're used to in the Ethereum ecosystem. So let's talk a little bit about how Scroll works. And this will be essential to understand why we need a bridge, something like Scroll Messenger, in order to, let's say, move assets or send data back and forth. So the Scroll architecture, like I mentioned before, we're a ZK rollup. So on the first layer, you can see here that would be Ethereum, where we have mainly two contracts: the bridge contract, we'll dive out in a bit, and the rollup contract. On our ZK rollup, we basically have two different two different layers. One is a sequencing layer. You might have heard of a sequencer. This is a node that processes all the transactions. So any user that interacts with Scroll, you would interact with it just like with Ethereum. It's just an RPC URL change. You would send any transactions to that RPC endpoint, and the execution node takes care of that. What happens simultaneously is that there's a different network of nodes, the proving network, that takes care of generating the proof. And not to dive into too deep, if you have any questions, feel free to approach me or drop them in the Telegram group. But simply put, what we do is transactions are batched into blocks, blocks are batched into chunks, and then we generate a proof for every chunk. And then the prover network, so this is done in a parallelized manner. The proving network generates a proof, an aggregated proof over all these proofs that are generated per chunk, sends it to the coordinator, and that's sent to the rollup node. And then the rollup node sends it to the rollup contract. And remember, in my story, I explained that if you have an L1 such as Ethereum, a rollup posts the batches of transactions on Ethereum, but Ethereum needs to understand, hey, are these correct or not? And so there's a smart contract on Ethereum that has the ability to verify the proof that a rollup, a ZK rollup, also posts, and that happens over here. So that's in a nutshell how the Scroll architecture works. And over here, you can see an overview of what each of these nodes do. One quick comment I would like to make is that our proven network today is actually decentralized. It is permissioned, but it's one of the things that Scroll is very much focused on, is that some components right now are centralized. Some components are decentralized. We're now on the road to making sure that everything will be decentralized, and our objective is to make sure that everything's decentralized and permissionless. So I briefly spoke about the architecture, and over here you can see a more deep dive of the transaction lifecycle. Again, we won't dive in too deep into this because I want to show to you guys how easy it is to deploy on Scroll, the main benefit of being EVM compatible, and then also dive into the bridge side of things. So over here, you can see a user, just like any other user, just like Ethereum, would send their transactions, the execution node batches them together, sends it to the rollup node, which posts it on the rollup contract. And side by side, you have the coordinator that takes care of that coordinates the prover network, and the prover network generates a ZK proof. It goes back, and the rollup node posts it on the rollup contract. You can, by the way, find all of these images on our docs, where we also have a good explanation. So the whole transaction lifecycle is documented. Probably something to mention is the phases of a transaction. So I'm going to go back and forth between the slides. Phase one is when a user submits a transaction, and what happens is that the sequencer basically processes these transactions and generates the block. This usually takes 1 to 2 seconds, and this is known as the pre-committed phase. At this stage, transactions are available on the ZK rollup. The second phase is when the blocks of transactions are committed on L1. So before we commit the ZK proof, we already commit the batches of transaction. So that would be, in this case over here, as you can see, in a matter of minutes, we commit the batches of transactions on Ethereum. And then the phase number 3 is when we have generated the ZK proof and committed and verified it on chain as well. And that takes roughly 10 minutes. Now, I just want to quickly pause here. You might think, hey, 10 minutes, that takes quite a bit of time. And this is something that is being improved over time, and we will see great things in the zero knowledge scaling space. But the comparison is not necessarily instant versus 10 minutes, but 10 minutes versus, for instance, when you look at optimistic rollups, where there's an arbitrary period. Now, if you know about the arbitrary period, if you don't know about the arbitrary period, I'm just going to briefly touch upon it, which is, as you might know, in an optimistic rollup, it's also a rollup commits the batches of transaction, and then there is an arbitrary period, meaning a set of predefined period that can be either 3 days, can be 1 day, can be 1 week, where anyone can challenge these transactions. And if there's a fraud, is there a malicious transaction, a fraud proof can be committed. So I know there is a whole debate about what the arbitrary period is, but let's assume that it's around 3 days or 7 days. That's basically the comparison to make, that it's 10 minutes versus the 7 days or 3 days that an optimistic rollup would have to be exposed to. So that was in a nutshell how Scroll works. Now, again, Scroll is an L2 ZK rollup, meaning it's a different blockchain network, but it commits everything back to a layer 1. And this is a very important point that I will touch upon again when we're gonna go and talk about the bridge. But now I want to quickly showcase to everyone how easy it is to actually deploy on Scroll. So I'm just going to show over here my code editor. I'm going to launch here, and I've set everything up. Oops. There, terminal. I just want to showcase the benefit of EVM compatibility. So this is just a basic smart contract that I grabbed from the Smart Solidity by Example website. If you don't know, it's a great resource for you to look at Solidity examples, and it's a basic Ether wallet. And over here, I have a deploy script that I will utilize to deploy this smart contract. I'm going to showcase the hardhat.config, and over here, I'm gonna utilize Truffle dashboard. Now, if you know a little bit about Truffle, unfortunately, it has been decommissioned, or they're gonna stop supporting it. I'm still gonna use it till the end. It's where my journey started, and I think it's a great tool to use. But we'll utilize the Truffle dashboard to deploy. And over here, I have configured the URL, the RPC URL for Sepolia Scroll, for local testing if need be. You can find all this information inside our docs as well. So what I'll do is I'll just compile my contract. Already compiled it, so it's nothing to compile. And then what I'll do is I will run this command, which will basically launch, send the bytecode to the Truffle dashboard to deploy on Scroll. So I'm just gonna go ahead and pull up first the Truffle dashboard so you guys can see it as well, and check if I'm connected to the right network. I am. By the way, a very easy way to connect to any network that you would like is Chainlist. So I'm just going to show that to everyone. If you type over here, Scroll Sepolia, over here you can see the correct network, and you can click add to MetaMask. I won't do that because I've already done that. If you add it to MetaMask, it's a very easy way for you to add the Scroll network to your wallet. And by the way, if you want to add it manually to your dev tool, this is a page of our developer quick start. And over here, you can see the RPC URL, the chain ID, everything that you basically need in order to connect to the Scroll network. So I'm just going to go back. I'm just going to go back and remove this. And over here, you can see the Truffle dashboard. I will go ahead and run the command. go back to the dashboard, and over here you can see that the transaction has been sent. I'm going to click on confirm. MetaMask pops up, confirm the transaction, and over here we can see the contract that's being deployed. We'll give it a second. And it's confirmed. We can view it on a block explorer. We've got an Etherscan block explorer, and over here you can see 15 seconds ago, it's a success, and we deployed our smart contract. So the same way you could do that if you've added to MetaMask the scroll network, you can utilize Remix, for instance, and it is as easy as that to deploy and scroll. It's just an RPC URL change. You copy, paste, and you basically deploy to scroll. If your favorite dev tool is maybe Ape because you like Python, or Foundry, you've been red-pilled and you like Foundry nowadays, it all works out of the box the same way as well. It's just an RPC endpoint change. So now that I've showcased on how to deploy on scroll, I quickly want to touch upon bridges. So I've mentioned that, am I good on time? Yes. So I've mentioned that, scroll is a different network, and blockchain networks are isolated, i.e. a network such as L1, such as Ethereum, cannot natively communicate with an L2 such as scroll. So enter blockchains. And here is just like a very simple example as a use case of what if you would like to transfer an asset from one blockchain to another. Well, the way that happens is through something called bridge contracts. So one bridge contract would communicate with another, and the specific methods of transferring the tokens, they differ. It could be that, there are wrap tokens being minted. There could be a different form of asset where this bridge contract actually holds specific assets, ERC20s, and sends them to the user's wallet once the contract has been triggered. But you might see something missing actually in this overview, because like I said, blockchains are isolated. So how do these two bridge contracts communicate? Well, that's usually through a third-party service or a relayer. So this is actually how a bridge usually works, is where a bridge has a contract on both sides, on a blockchain A and a blockchain B, also refers sometimes as a source blockchain and the target blockchain. So the target blockchain is where you're going, and then utilizing a relayer, which is usually a service that listens to both contracts and makes sure that communication either in one way or both ways is possible. And that's what the scroll messenger is. The scroll messenger is a bridge. And so over here, what you see is what I'll showcase to you guys in the smart contract is we're going to send a message from L1, so a testnet Sepolia, to the scroll testnet, and then we'll send a message from the scroll testnet to L1 back to Sepolia, and we'll take that step. We'll do that step by step. Now, very important to note, when I say message, I mean that's arbitrary data, meaning it's just any data. If you would like to transfer ERC20 assets, if you would like to transfer an NFT, that's all possible, and we've got specific guides for that. Right now, I will showcase to you the bare bone version of this, i.e. any data that you would like to send from left to right, i.e. in this case, from Ethereum to scroll. So what happens over here is, and I'll show the code in a bit, we have one smart contract, and this can be any smart contract. In this case, it's called the operator, that we have deployed on Sepolia. And what we want to do is say, hey, from this operator, we want to change the message that is on L2 inside our greeter contract. Now, what will happen is that we will tell this smart contract, hey, talk to the scroll messenger, the bridge contract, and we want to target this smart contract, and then we send an arbitrary piece of data. Now, when we do that, we send a little bit of ETH, and that has to do with the fact that when you send a message or data from an L1 to an L2, the transactions on L2 have to be processed, and the L2 messenger needs some ETH in order to update the state of, in this case, the greeter smart contract. Now, you might notice saying, hey, I'm not seeing the third-party relay. And that's because when we go from L1 to L2, I'm just going to go back a couple of slides. Over here, you can see that we have in our sequencer on L2 the sync service. And what this does is it listens to the bridge contract and it pulls in any L1 transactions that are committed on the bridge contract. And this is the scroll messenger contract on L1. So that's why in this specific overview, you can't see that, but this is a simplified overview. So when we go back, I'm going to pull up Remix. Remix over here. And over here, I have a set of 4 contracts. I'm just going to go to this one. And I'm just going to walk everyone through the set to the set of contracts that deliver the message from L1 to L2. So I'm just going to open these contracts. There's this contract and this contract. So over here, you can see we have a greeter on scroll. So I'm going to go back. That's this one. This is our smart contract on L2. And the greeter on scroll looks something like this. It's a very simple smart contract. It has a variable where it says, where with a string, it says hello world. And over here, you can see a function that allows this variable greeting to be updated. Now, if you pay close attention, you can see that the variable is actually called hello world. But over here, when I call the variable, it says hello world from Sepolia. And that is because prior to this session, I actually sent a message from L1 to L2, and I'm going to show you how I did it. I won't do it during the workshop, being that it can usually take up to 4 or 5 minutes, up to 10 minutes. And at the risk of, during a demo, everything breaks, I'm just going to showcase how it works. But again, feel free to approach me or any of the team if you run into something. So again, we have a greeter contract on L2, and that's where we want to change state. When we say change state, we just want to update some data, some arbitrary data. So I'm going to go and showcase the operator contract on Sepolia. So this is on L1. And what this contract does is actually a very, very simple bunch of things. What it will do is we need to tell this contract what the smart contract address of this L1 bridge contract is. So that's what I've done over here. If you're wondering where you can get this information, over here in the docs, we have 2 places. Oh, I'm sorry, I need to remove, I need to just lift this. Yeah, we have in our docs all the contracts that are available on all our scrolls smart contracts. So over here, you can see the L1 and L2 messenger. In this case, I need the L1 messenger because remember, I want to send a message from L1 to L2. So what I do first is this contract, I copy and paste it in the scroll messenger address. The second thing I need to tell the scroll bridges is which smart contract I'm targeting on L2. In this case, remember, we want the greeter contract, and that is the smart contract over here. So I copy and paste that address. We send 0 value because in this case, we're not actually sending any ETH to the target address. And over here, you can see the greeting that I sent, and we set a gas limit. This gas limit is pretty high. I mean, 10,000 would work as well, but and the only gas that actually be utilized will be spent, and then the remaining will be sent back. And so over here, you can see that as soon as I click here, transact, which I won't do right now, basically what happens is that the state on L2 will be updated. And over here, you can see that's what I did a moment ago. Quick side note, again, when we send it from L1 to L2, we want to send some ETH along. Doesn't need to be a lot, but we want to make sure that our transaction doesn't revert on L2. And so we send a little bit ETH to L2, along with the smart contract so the transactions can be processed. Something that I've noticed right now, I haven't mentioned, is the native currency on Scroll is ETH. And again, EVM compatible, staying close to the Ethereum ecosystem. So when you develop on Scroll, you use ETH as a native currency to pay your gas transactions. The way you get your ETH there is through the Scroll bridge, or if you're just want some testnet ETH, remember to join our Telegram group and we will send you some. So this is how we send it from L1 to L2. Now, if you go back to our slide and we want to send it from L2 to L1, there's one addition that we need to consider. Now, when we send the message from L2 to L1, Ethereum needs to know, hey, first of all, is this transaction correct or not? And remember, when we look at all the transactions and then messages at the end of the day is also a transaction, they're batched together and they're sent to L1, so the ZK proof is generated for that as well. But also on L1, we want to make sure that the user, the correct user, is allowed to withdraw any data. So in order to do that, on L1, we're going to need something called Merkle proof. And so I'm just going to go back to Remix. And over here, what I'll do is I'll showcase a part of our doc, which is important to just dive in if you need any more information. But basically what we're going to do is we're going to make a call. We have a relay service for this. And what this does is over here, you can see the API call that you can make is by sending the smart contract address of your operator. You will make an API call, and I'll show you what it looks like. It looks like something like this, and that looks like a lot. I'm just going to increase the size of my screen. And basically what it will give you back is all the transaction data that you will need to fill in a specific page. I'll show you that in a bit. You will need to tell the L1 messenger, smart contract messenger, hey, I've got this transaction was either sent for me or is sent by me, and I have the proof, and that starts over here. You can see proof. I have the Merkle proof to withdraw this piece of data, and that will allow to update state. And I think I've got a couple of minutes, and then I'll show you guys a video of how it exactly looks like. So over here on the Etherscan Sepolia, if you click on the link inside the docs, it will take you to the messenger contract, and over here you fill out all the data. And I hope I'm not walking through this too quickly, but over here you can see, I'll quickly showcase the video that when all your data is filled in, what you can do is click on write, and that will send the transaction. And over here, and this can view the transaction. And then once the transaction is sent, as you can see over here, I'm just going to click back again. Once the transaction is sent successfully to the L1 messenger and the proof has been submitted, over here you can see I click reading, and it changed from hello world to hello from scroll. All right, with 1 minute left on the clock. I'm not sure if there are any questions. Would love to answer some. I hope this was useful. I know there was kind of like a speed run, but again, drop the Telegram link. Any questions you have, feel free to approach us. We would love to help you. Super stoked to see what you guys will build.